Okay, this video is about some theorems about roots of polynomial equations. It's section 6.5 in your book. So first we're going to look at this equation and we're going to find the zeros of this equation using GeoGebra. So if you look at GeoGebra, I have it graphed here. It's pretty obvious that the zeros are at -2, 3, and 4. So we can see that pretty easily. Those are the zeros of this function. If I plug in -2 for x, I get 0 for y. Same thing for 3 and 4. So with those being the zeros, I want you to think about what is the relationship between these numbers and 24. So -2 times 3 times 4 gives you -24. And what you'll notice is that these numbers are all factors of 24, and that's not just a coincidence. So there's this thing called the rational root theorem, and it tells you that if a number is a zero to a polynomial equation, it is a factor of the constant term, the last one, that's this, the last term, divided by a factor of the leading coefficient. Alright, so the constant term in this case, like I said, is 24, and the leading coefficient in this case is 1. So if it's going to be a 0 to this polynomial equation, I have to be able to write that 0 as a factor of this constant term divided by a factor of the leading coefficient. So the factors of 24 are 24, 12, 6, 4, 3, 2, and 1. So any combination of these, and plus or minus for all of them, because -2 is a factor of 24 also. The leading coefficient is 1. So plus or minus 1 are the factors of the leading coefficient. So these are the only possible rational roots to this polynomial equation. Things that can be written as a combination of this. Well, anything over 1 is just 1, so I actually don't need this bottom. Plus or minus 24, plus or minus 12, plus or minus 6, 4, 3, 2, and 1 are the only possibilities, and we see the actual roots are factors. You have 3, 2, 3, and 4, and plus or minus in the case. So let's do an example of this. Okay, so we're going to find the rational roots of this equation. So the first step is to list all the possible roots, and then the second step is to test them. So all the possible roots are they have to be in this form. If it's going to be a root, it has to be a factor of 3 divided by a factor of the leading coefficient, which in this case is 1, factor of 1. So the factors of 3, 1 is a factor of 3, and 3 is a factor of 3, and then the factors of 1 are just 1. So 1 over 1 is 1, and 3 over 1 is 3. So these are the only possibilities, plus or minus 1 and plus or minus 3. Those are the only possible factors of this equation. So let's test them and see if we can find whether they're actual roots. So I'm going to use synthetic division. So here's those are the coefficients of this equation, and I'm going to test, let's try 1 and see if 1 works. Remember, if it's a root, then after we're done with synthetic division, we'll have a 0 here, because there would be a remainder of 0, which means it's a root. So let's bring this number down. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. -3 plus 2 is -1. -1 times 1 is -1. We end up with -4. So 1 is not a root. So now we have 3 others to test. We can test -1. So 1, -1, 0, 0, -3, 3, 0. So we have found a root. -1 is one of the roots. Okay, now I'm going to test and see if 3 or -3 is also a root. So 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. Not a root because we don't get 0 here. Okay, let's try negative 3. 1, negative 3, negative 3, 9. Again, not a root. So negative 1 is the only rational root. There are other roots, but they are not rational. So negative 1 is the only rational root. Okay, so then again here, the only possible rational roots would be the factors of 1 over the factors of 1. So plus and minus 1 are the only possible rational roots for this equation. So then if you test them, you can find out if they are actual roots. Okay, so then now we're going to find all the roots, not just the rational roots, but we're going to use the rational root theorem to find all the roots. So the possible rational roots are the factors of 1 over the factors of 2. So that's plus or minus 1. The factors of 2 are plus or minus 1 or plus or minus 2. So 1 over 1 would give you 1, and 1 over 2 is plus or minus 1/2. So these are all the possible rational factors for this equation. Okay, so I'm going to try 1 first and see if it works. Doesn't work. So 1 is not a rational root. I'm going to try 1/2 now and see if 1/2 works. So 1/2. 0, 0, 2, 1, 0. 1/2 is a rational root. So we found 1. Okay, now we got to find the others. Well, now we have 2x squared plus 0x plus 2 is what our equation has reduced to. So now we can solve this quadratic equation several different ways, the easiest of which is by subtracting 2 from both sides, and you get 2x squared is equal to negative 2. Divide both sides by 2, and you get x squared equals negative 1. Take the square root of both sides, and you get x is equal to plus or minus the square root of negative 1, which is I. So 1 and plus or minus I are the other two roots. So we have found all the roots of this equation, 1/2 and plus or minus I. Okay, now I'm going to talk to you about conjugates. These are irrational conjugates, and it's a conjugate if it can be written in this form, a plus the square root of b and a minus the square root of b. So an example of that, 2 plus the square root of 3 and 2 minus the square root of 3 are conjugates. So this is the irrational root theorem. What it says is if you have a plus the square root of b as a root of an equation, then a minus square root of b is a root also. So an example of that, if we know that 1 plus the square root of 3 is a root, that means 1 minus the square root of 3 also must be a root. If we know that negative square root of 11 is a root, we know that positive square root of 11 must also be a root. So these are two additional roots. So here, if 2 minus the square root of 7 is a root, 2 plus the square root of 7 is also a root. If positive square root of 5 is a root, then negative square root of 5 must also be a root. The same thing is true with imaginary numbers. So a plus b times I and a minus b times I are conjugates. They're called complex conjugates. And the same thing is true. If a plus bi is a root, a minus bi must be a root. So here's an example. If 3 minus I is a root, then 3 plus I must also be a root. If 2i is a root, negative 2i must also be a root. If 3i is a root, negative 3i is a root. And if negative 2 plus I is a root, then negative 2 minus I must also be a root. These are all conjugates. So the conjugate of 3i is negative 3i. The conjugate of negative 2 plus I is negative 2 minus I. Notice it's not 2 minus I. That would be the additive inverse. If you add those two together, you get 0. If you add two conjugates together, you do not get 0. Unless the first part is 0. So 3i plus negative 3i is 0. But if you have a plus bi and a minus bi, what you get is 2a if you add these two things together. well, if a is 0, it ends up being 0, but most of the time it wouldn't be 0. Okay, so if we were going to find a third degree polynomial with roots at 2, 3, and -1, that would mean x minus 2 is equal to 0. That's a root at 2, because that means x equals 2, x equals 3, and x equals -1 are the roots. Well, if you subtract 2 from both sides, you get this. If you subtract 3 from both sides of the second equation, you get that. And if you add 1 to both sides of this last equation, you get this. So these three things are true. X minus 2 equals 0, x minus 3 equals 0, x plus 1 equals 0. And these are factors of that third degree polynomial equation. So I could write it like this: x minus 2 times x minus 3 times x plus 1 is equal to 0. I could FOIL this out, and I would have a standard form for a polynomial equation, but this is good enough for my purposes here. Okay, now what we can do with a more difficult example, we want to find a third degree polynomial with roots -2 and 3i. Well, you need to know all of the roots. If it's a third degree polynomial, it has 3 roots, and we only see 2 of them. The third root is the complex conjugate of 3i, which is -3i. So now we need to write these as factors instead of roots. Well, again, if x equals -2, 3i, and -3i, the factors are x plus 2 equals 3, x minus 3i equals 0, x plus 2 equals 0, I said equals 3, excuse me, and x plus 3i equals 0. So these are the 3 factors. So if I wanted to write a third degree polynomial equation, I would write it like this. Now I could go ahead and FOIL this out, and I would get a third degree polynomial equation, but I'm going to skip that for now because I'm going to do it on this problem. Okay, so if I have a root at 3 and a root at 1 plus I, then my other root is at 1 minus I. This is the complex conjugate of 1 plus I. So my roots are at, my factors are at x minus 3, x minus 1 plus I, and x minus 1 minus I. Because if x is equal to 1 plus I, then if I subtract 1 plus I from both sides, I end up with this. All of that is equal to 0. Now what I'm going to do is going to be kind of long-winded, but we're going to go ahead and write this out in standard form. So we're going to multiply this out. All right, now very important strategy. Multiply these two first. If you don't multiply those two first, you're going to end up with a lot of terms that have I in it, and it makes it really easy to make a simple mistake. So we're going to multiply these two conjugates, and what we'll see is the i's are all going to cancel out, and we'll be left with a fairly normal quadratic. So you do x times x, and you get x squared. You do -1 plus I times x. Let me undo that. -1 plus I times x, and you get -x times 1 plus I. Then you do x times -1 minus I, and you get -x times 1 minus I. And then you do -1 plus I times -1 minus I, and you get a positive 1 plus I times 1 minus I. Okay, so now we need to multiply all of this stuff out. You get x squared minus x minus I times x, if you distribute this -x, and over here, this is a minus sign here. You get -x times 1 is -x, -x times -I is a positive I times x, and you can already see that these two terms are going to cancel out. Okay, and then let's go ahead and finish this off. 1 times 1 is 1. I times I, -I is -I squared. I times 1 is I, and -1 times I, -I times 1 is -I. So these two also cancel out. So this term cancels with this term, and these two terms cancel, and this is what we're left with. negative I squared. I squared is equal to the square root of negative 1 squared, which is equal to negative 1. So I squared is negative 1, so we have x squared minus x plus 1 minus I squared, which is negative 1. Okay, so this is x squared minus 2x plus 1, which is x squared minus 2x plus 2. Alright, now that's what these two terms multiplied together equal. You should not have any i's left, any imaginary numbers left. If you do, you made a mistake. If you multiply complex conjugates together, factors like this, you should end up with only real solutions. Okay, so here we go, and then we got to multiply that times x minus 3. So if you multiply each of these terms by x first, you get x cubed minus 2x squared plus 2x. Then if you multiply each term times negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x is a positive 6x. And negative 3 times negative 2 times positive 2 is a negative 6. So you end up with x cubed minus 5x squared plus 8x minus 6 equals 0. This is the polynomial equation with roots at 3, 1 plus I, and 1 minus I.